topic is units and dimensions. So we first we'll look at units, right? In order to measure a given physical quantity, right, we need a standard unit for that quantity, correct? So what are units, right? They are the standard unit of a physical quantity. So normally the measurement of any quantity specified, it's in two different parts. First part gives you how many times that standard unit is measured, okay, and the second part gives you the name of that unit, right? So let's write there two parts of measurement. So part number one, right, is how many times, and part two is the name of the unit, right? So for example, if we say length is 5 meters, right? So that 1 meter is the standard length which is measured 5 times. So how many times is measured in ಇದು ಹೇಳ್ತದೆ. ಅದರ ಜೊತೆಗೆ it also talks about the name of that unit. So as soon as we see, right, meters, we understand that it is, right, the length, right? Why it is so? It is because we can say there are basically two types of units. The first one is fundamental units. So fundamental units are basically the fundamental, they are the units of the fundamental quantities. Okay, there are only 7 fundamental quantities in physics, so every fundamental quantity gets one special unit given, right? They are unique, they are completely independent. Okay, so this can be mentioned as independent units assigned to the fundamental quantities, right? So there are basically 7 independent or 7 fundamental quantities to which we assign fundamental units, right? Could be length is length, mass, time, current, temperature, amount of substance, and intensity of light. So these are the 7 different, they are not dependent on each other, they are completely independent, right? So length and masses are not dependent on each other, but volume and length, they are dependent, one is dependent on the other, right? So volume is nothing but length into length into, so right, we use meter cube for say volume, whereas the meter is itself a fundamental, the unit, fundamental unit, Okay, so we can see that the fundamental units can be used to derive the other units, right? That is why it is called as the fundamental units can be used to derive the other units, so that those quantities are called as derived quantities, right? Next, second type is derived. This is derived units. So the derived units are units derived by using the fundamental quantities are called as, right? We are calling them as derived units. They are derived from fundamental quantities, and the units of those quantities are called as derived units. All right. Now, for every measurement, right, we are going to follow the SI units. This is standard international. SI stand for International Standard of Units, right? So now when we define, say, fundamental units, we are always going to follow a system called as standard international, right? uh, so internationally recognized system it is. Okay, so for example, let's write the different fundamental quantities and their units. So first one is length. So the SI unit is in words meters, meter. So the symbol for that will be M, small letter M. So almost all symbols will be using the small letters most of the time. So the second one is mass, kilogram, and this is kg. Then we have the third quantity, time, which is independent of any of the others we write on this table. So time measured in seconds, so unit is s. Then we have electric current, so this is measured in ampere. Unit is, see, this is capital A. All right, then we have temperature. All right, this is measured in Kelvin in the SI units, so this is capital K. Okay, then we have the amount of the substance measured in mole. So unit is mol. Okay, then the light intensity, this is measured in candela. So unit is cd. So using these standard units, we can measure the other units, right? Such as say force, right? Also maybe velocity, right? Acceleration, area, volume, density. All these are the derived units because you can see them in the units itself. When we mention the units of the derived units, you will see either of these units coming up over there. Okay, something like kilogram per meter cube, right? Meters per second square, right, etc. You can see that that's what is the unit, and these units also use a prefix, right? So the standard prefixes in SI, that's also very important. Prefix of units in SI. Okay, so we'll start from the right. So 10 to the power, right? It's a 10 to the power numbers, right? In order to start the length of the given, what do you call, data, right? We will try to make it into a 10 to the power number. So this is important. If you have 10 to the power 9, this is called as, sorry, this is giga, Giga, right? So the notation for this is capital G. Okay, then 10 to the power 6 is, this is mega, right? So that is unit is capital M. Okay, we measure the frequency in this range, right? This is, if you write 78 megahertz, right? 78 megahertz, mega stands for, this is actually 10 to the power 6, 78, the M stands for 10 to the 6 over there. Okay, very similar to this. Let's go to the next one, that is 10 to the 3 is called as kilo. Unit is small letter k. Okay, then 10 to the power minus 2 is the other standard. This is called as centi, small c. Then 10 to the minus 3, this is milli. So millimeter is 10 to the minus 3 times meters. So unit is, the standard notation or a symbol is small letter m. Okay, then we have 10 to the minus 6. 10 to the plus 6 is mega, 10 to the minus 6 is micro. So for micro we use this notation called mu. Okay, then 10 to the power minus 9 is actually nano, right? So the notation or a symbol is n. We even go to 10 to the minus 12 sometimes. So this is called as a pico. So small letter p. Okay, so all these prefixes, they are very standard in the SI units, right? You can use any of them as and when needed, and that is absolutely fine. Okay, after the units, right, we'll see the different units later. We'll make a table. Okay, that's going to help us throughout the course, right? That's the first thing, and then now we'll define what is called as a dimension. Right. So dimension of any physical quantity any physical quantity uh, is it is the powers to which the fundamental quantities must be raised to represent the given quantity. Okay, so example, let's go for density. Right, we know that the density can be measured by what? By mass per volume. Okay, now this means volume is actually a derived quantity, so I'll write the mass is measured as a fundamental quantity is mass only, but volume you have to use the length three times, length into length into length, length into breadth into height normally. So that's, once again you see that length itself has been used in different ways, right, three times. So this means, right, the number of powers that you raise is, right, you can see here this is mass is raised one times and length is raised three times in the denominator, but when I write it in the numerator it is minus 3. So the unit will be the unit of mass, maybe kilograms, and the length is in meter, kilogram per meter cube. We can write in that, right? So, but you see, the standard way of writing this is this is the unit. So when I write in a square bracket, we write it in the units of density. Unit of density is equal to, this is the unit of mass, you write capital M. Okay, so generally mass is M, length is L, and you may require time as well, so T to the power T, but right now T is not there, so M to the 1, L to the minus 3 is how you write a physical quantity in terms of the base quantities. Okay, so when I say base quantities, there are three base quantities. Base quantities of, or base quantities are, let's write in that way. So M for mass, L for the length, and T for the time. Right, out of the fundamental quantities, these three are referred as the base quantities, and using the base quantities we always write, right, the units on the dimensions of any other physical quantity. Okay, but you see it's not that, so most of the quantities, physical quantities, can be represented by base quantities, that's all, but not all. So for example, sine theta, right, if you take sine theta, right, I cannot represent it using any of them. It's not a mass, it's not a length, it's not a time, right, it is something different which is angle, correct? So some units, like some of the quantities like that, right, may not be able to, you may not be able to use the base quantities to define them, but yes, most of them we can. Okay, then now let's make the list of physical quantity, the SI unit, and followed by the dimensional formula like this. For everything, if we remember, we can solve any of the problems based on this. Okay, it's a table. Now we'll start with the first quantity, that is velocity. So velocity is actually measured as the displacement, right, divided by time, right? So what is a SI unit, right? The unit for display velocity is, this is measured in displacement, you see it is meters, divided by time has a unit ms, m meters per second, or you can also write it as ms inverse. So what is the dimensional formula for this? It's in terms of mlt, you are normally writing no mass, m to the power 0, l, yes, there is length, power 1, and time, yes, it has a time component, seconds I can see there, it's power minus 1. So m to the 0, l to the 1, t to the minus 1. Okay, now similar to this, next we need, say, acceleration, right? Acceleration is measured as the velocity per time. Okay, so that means this is measured in, velocity is meter per second, right, divided by second. So this is meter per second square, or this is ms minus 2, right? So this means this, the equation or the dimensional formula can be written as m0, l, and t to the minus 2. Then we go for the third quantity, which is called as force, right? Force is going to have, the equation is mass into acceleration, right? So this means it is, mass means kilogram, right, multiplied by acceleration. So mass into acceleration, in the sense this is kilogram meter per second square. Okay, kilogram meter per second square. There is a special name given to this quantity as Newton, that is capital N, right? So but the dimensional formula still remains same. Okay, so kg is a mass, so there is mass 1 into, there is a meter, so this is length, and time raised to the power minus 2. All right, so that's the force. Then let's go to the next quantity. This is a work. So work is calculated as, see, this is a derived one. We derive the work as force into distance or displacement. Force into displacement. Now what's the unit of force? That is kilogram meter per second square, into displacement is another meter, correct? So this becomes meter square, kilogram meter square per second square. Or the original one, you can, if you see the kilogram meter per second square, then that will be a Newton, and I'm multiplying by the meter distance. So this is also called as Newton meters, Nm, right? There is a different name given to the measurement of work, right? Which is the fundamental unit of energy. Work and energy are having the same this thing called, it's a J for joule, denoted by capital J. But let's write the dimensional formula for this, right? Dimensional formula for work is, there is one mass kg, length is raised twice, meter squared, time is raised to the power minus 2, that's why ml square t to the power minus 2. All right, then, so you see joule is not fundamental unit because it has ml squared and t also has some other term. So now let's define the energy. This is, right, directly measured in joules, and we know that its dimensional formula is ml square t to the minus 2. Previously we have written this. Okay, after energy we have the next quantity called torque. Okay, so torque is nothing but the force into distance. So force into distance, so this means force is in Newton, distance in meter, so Newton meter. We already know that the Newton meter is defined as m l square t to the power minus 2. Then the next standard one which we are going to use is power. How you measure power? Power is work done per time. So this is work divided by time. So this is actually work is measured in joules per second. So joules per second is actually has another name called WATT, denoted by capital W. So this is joule. Joule has ml square t square. I'm going to divide this by time once again. So t gets another power. So this is m l square t to the minus 3. Okay, then the next quantity which we are going to use is called as momentum. So what is momentum? It's mass into velocity. So mass is kilogram, velocity is meter per second. So this has the units like there is one mass, there is one length, and t to the power minus 1. Then another quantity is called as impulse. This is nothing but force into time. So we know that force is measured in Newton, time in seconds. So this is Newton seconds. So in the units of Newton, I have to reduce the power of seconds. So one power is reduced for second. We actually have mlt to the minus 2, but there is a multiplication of s now, that is a second. So m L t to the minus 1. So if you see the units of impulse as well as the previous one, that's a momentum, they remain same. Okay, then this is angle. So this is the length of arc divided by the radius. So this is measured in radians, right? So what will be the, it's not mass, not length, not time. So in terms of fundamentals, I cannot write, right? So then there is another quantity called strain. Strain is nothing but, you can measure it as delta L by L. So both have the same unit. That's also delta V by V. Same unit. Units will cancel. So you see that this particular quantity has no units. So when there is no unit, you cannot write it in terms of them. So you write M0, L0, T0. Okay, then the next physical quantity is called as stress. This is the force per area. It's called as stress. So measured in Newton per meter square. So the unit becomes, for Newton we have ml t to the minus 2. So I'm reducing. So first let's write for Newton. Newton is ml t to the minus 2. Divide this by the L square. So L square means L, when this goes to the numerator, it becomes L minus 2, right? Already there is a plus 1. So plus 1 minus 2 is minus 1. So our quantity becomes M L to the power minus 1 T to the power minus 2. So that is the unit term, the dimensional formula for stress. After stress, we have the quantity called pressure. This is also measured as force per area. So force per area, we know this is Newton per meter square. So that is M L to the minus 1 T to the minus 2. Okay, then after pressure we have the next quantity. It is called as modulus of elasticity. So equation is stress by strain. So out of which the strain has no units, so only the units of stress will come. So if you look at the stress which we have written just now, so it has a unit Newton per meter square. Okay, so Newton per meter square, we can write it as m to the 1, L to the minus 1, and T to the minus 2. Then the next quantity is called as the frequency. This is 1 divided by the time period. So that's the equation. So time is divided. So this is S inverse second per second, or that's called as hertz, Hz. Okay, so this means it has no mass, no length, but only time to the power minus 1. Then let's go to the next quantity. This is called as moment of inertia. How do you measure this? This is measured as mass into distance square. So mass into distance square means mass is kg, distance square is meters square. So the unit is m to the 1 L square and t to the 0 is moment of inertia. Then the next physical quantity, this is also a derived quantity called surface tension, measured as force per length. So unit Newton per meter. So the Newton has one length. So since you are dividing by length, that length is gone. So you can see Newton has m L t to the minus 2. So dividing this by not t, sorry, dividing this by L will actually cancel this L. So I don't have L now. So m L0 t to the minus 2 is the required dimensional equation. Okay, then the next quantity is the angular momentum. Okay, angular momentum is directly calculated as kilogram meter square per second. So this is directly measured in kilogram meter square per second, or kg m square s to the power minus 1. So what should be the dimensional equation for this? M, there is a mass, right? There are two lengths L square, 1 second in denominator. Okay, so in this sense we can always try to measure the various dimensional formula from their basic equations. Okay, now so we should know, even if we don't know the dimensional formula of certain quantities, we should know how to derive. Okay, so that can be easily done. Now we already have done that, right? But that can be done easily, right, as per the requirement. Okay, now So for example, let's take some of the quantities. Let's say I want to measure, or I want to find the dimensional formula for the following. Say we want to start with, right, uh, say density. I know the answer already, it's there in the table, but we'll first write the formula, that is, this is mass and volume. So what do? The dimensional formula of density is equal to dimensional formula of mass divided by, this is dimensional formula of volume. So mass has m, no length, no time, divided by volume has no mass, length 3, and time 0. Now the actual formula can be written in this form. So m cancels, both are m. There is one m in the numerator, no m in the denominator, m to the 0. So this remains as m itself. L0, denominator is L3. So L in the 3 L's in the denominator goes to numerator as -3. So this is L minus 3. T to the 0 is the required dimensional formula of density. Okay, like this we need to calculate all the other quantities.